Good afternoon, everybody. I'd like to welcome you to this seminar we're having today with some very distinguished former LASP members.
Not all former.
Excuse me. Yes, I already screwed up. You know, one of the neat things about LASP is our involvement with very young students, and I've been feeling like I'm the ancient person. With this distinguished guest, I'm feeling more in the middle now. Very nice for a change. This all started after Dr. Barth passed away. Karen came to my office and said, you know, we are losing history. We don't capture it somehow. We're losing what started LASP, what's made LASP great. And again, there's a lot of people that walk into LASP and it's already here, and you don't realize what it took to put here in place, and the kind of work that these people have done to get us where we are today, where stuff like operating a Kepler is routine. Operating 100 instruments on MMS is just another small step in our progress. It's an amazing history that we have here. So I want to thank Karen very much. Karen's been a very strong rounder-upper of all this stuff that we have put together. A lot of the things we have on display from Karen. And thank you very much, Karen, for doing all the work. Tom Mason in the back has also helped a lot. He's filming, but also he put together the slide presentation that's kind of going to be running in the background as our panel talks. So my job is to kind of stay out of the way once we do introductions. So I'm going to go around the room and just, what I'd like to do, it might be easier if we take turns and just introduce yourself and say kind of what role you had. I know a lot of you had multiple roles here, but kind of what your role was when you came to LASP as it evolved, and take it away, Phil.
Okay, I'm Phil Evans, and I started as a student in the fall of 1970, and started working with the computer system they had there, and just received their second one, the PDP-12. And the guy who hired me left in about a year, and so that left me in charge of all the computers. And they grew and grew and grew over the years. And after 40 years of it, I finally retired. But it was always very interesting, all the new systems, new languages, new operating systems, and also communications. We had a lot of the data communications went through equipment that I was responsible for, networking, everything like that. And I enjoyed all 40 years of it.
And he is the maker of all the models that are hanging up in the lobby.
Absolutely. Right.
Get that. Thank you. Alain?
Well, you all know me, yes, because I still work here. So I'm Alain Jouchoux. I came to LASP in 1974, working for a French laboratory on the WWII spacecraft. I stay here. I was running basically the instrument. We have a lot of guest investigator and the co-I investigator French here, and I was running the instrument for them here with the Alain and so forth with the LASP group. I came back. I left in 1977. Came back in 1984 to work on the SME spacecraft, do some ground software on the command side. And then I work on the Oasis software, which I'm still working on. I'm the only one still live, at least at LASP, that is running, is working on the Oasis software, the core. Other thing I've been doing at the lab, I wrote the flight code for the UVIS instrument on the Cassini software, and I'm running the UVIS instrument on the Cassini spacecraft. I'm also a flight controller on QuickScat.
Thanks, Alain.
Hi, I'm Margi Klemp. I came to LASP in '72 to work on the OSO-A project with Alain and David Stern. The first thing I did was to work with David on the SOL language, the solar observing language, which was somewhat ideal-like, I would say.
It's a pre-ideal.
A pre-ideal type of language that the user could manipulate and display data, science data. And also worked a little bit on test and calibration procedures for the UV instrument that was on Solstice. And let's see.
Don't forget to resist.
Well, yeah. Yeah, I started working part-time with Phil Evans too, to do system administration, certain parts of system administration. Worked on Oasis. And let's see, there's a number of different projects that I worked on, doing data formatting, and Oasis, we started working on a user interface development project, which was based on TAE Plus, which I guess you don't even use anymore here.
We still use it on the regular mission, on the new mission, it's yes.
Yeah, but there were a lot of projects that happened to enhance the TAE Plus workbench in order to display direct manipulation objects with TAE and then ultimately with Oasis. Let's see. And towards the end, I was here until 93, 94.
Yeah.
And 95 maybe. I don't remember. 10 years I've been gone, something like that. But anyway, we did have another contract with NCAR to try to integrate the TAE Plus user interface with their PolyPaint 3D visualization tool. So it's all been different and enjoyable, and great people to work with.
Thanks, Margi. Dave, and just a reminder, there's no microphone for you guys, so
Okay.
kind of project a little bit.
Well, I'm David Stern, and I started work at LASP in September of 1969. My first boss is that guy right there, Ian Stewart. And he was fresh off the boat, right? And he gave me a metal tray of Fortran cards this long. He said, "Here." I had no clue what it did. No, it's atmospheric models, and I spent probably first 3 or 6 months working on that, I guess, and then I moved on. I think, does anybody know when Gene McCullough left?
Yeah, I think it was 67.
No, because he was here when I was here, I think.
Well, they published that paper in 69, but I have the feeling
Yeah.
it didn't come out until
Well, anyway,
afterward.
they
Yeah.
needed somebody to do software for the little computers, and I got picked, and that was really the most exciting thing I'd ever done before, because if you were at the university in those days, which I was, they had a CDC 6400 with all these guys with white coats and layers of security, and you couldn't get near it. And you basically put your card deck in a cubby hole, and then you came back anywhere from 3 to 24 hours later, and then you got a syntax error on this card. Seriously. So,
Yeah,
Yep.
yeah.
and so the PDP-8 was just an amazing piece of equipment. You could touch it. Had switches. It had lights. It had a teletype that was like a pinball machine, and I just took to that like a duck to water, I guess. And then I started working on the gene system, and basically it evolved into the Mariner Mars spectrum editor system, which then evolved into Rufus, which was a system for the PDP-12. Randy gave me, PDP-12 was a laboratory computer that was a mixture between a PDP-8 and a Link computer. And this is the whole manual that told you everything you need to know about it. And then it evolved to Sol, and then IDL. And I left LASP in 1977, and even after I left LASP, Dr. Barth was very good to me, and he gave me a contract to develop what became IDL and continue to patronize my company, and it's been very good. So, thank you,
Thanks.
LASP. And Dr. Barth.
Yeah. So I'm Randy Davis. I came to LASP in the probably June of 1969, right after I had completed my sophomore year. And first thing I did was work on the spacecraft that's downstairs, Mariners 6 and 7, which at that point were halfway on their way to Mars. And so I worked on that project and then went on and worked on Mariner 71 and a variety of others that I'm sure we'll touch upon as we go along. I worked on SME and did a lot of work on SME, and then in 1991 I became the director of mission operations and information systems, and stayed in that position for 15 years until I retired. And overall, I calculated recently, I participated at LASP, I participated in 28 different missions, 22 of them substantively, and everything, my joke is that I worked on everything from NASA's biggest projects, the space station, to the littlest, like SNOWY and SME. So the little ones were more fun, frankly, than the big ones. So.
Thanks. Sabine?
I'm Sabine Schaffner, and as everybody who is sitting at this table knows, I do not know about computers, so I'll tell you about science. I'm a retired scientist. I had met Bill Rentz, who was the former director before Dr. Charles Barth, and when I came from England in 1954. And Bill Rentz had known that I had worked at the observatory, so when I decided I would come back to work after my children were a little bit older, because in those days women stayed home with their children, Bill Rentz hired me to work on the Orbiting Solar Observatory 5, which at that time was in the planning stages, being built at Ball Brothers. And then, after less than 2 weeks, Dr. Charles Barth arrived from California, and he asked me to join his group. And I was delighted too, and have been very pleased that indeed went in that direction. So from then on, I worked on the orbiting geophysical observatories. They were a series of observatories to study the geophysics of the Earth in different types of orbits. The first one I worked on was a polar orbiting called OGO-4. And at that time, we had no capabilities here of processing just about anything. I would go to Washington, I would go to the Space Center and ask for the spacecraft to be interrogated because it had a multiplex system that could only be downloaded in different stations, one in Australia, one in Spain, one in, I'd forgotten, maybe somebody will remind me.
Goldstone, California?
Oh yeah, certainly California, but I think there was one somewhere else in the Indian Ocean. And so I would go to Washington and ask in a very primitive way that I would like to have the following information played out of a spacecraft when it happened to be over a particular station, because that was the only way we could get information, nothing like what came later. And what that meant was giving instructions, getting these immense rolls of strip charts. They were about this wide with many of the different
Channels?
Well, the different articles, but it was for Lyman alpha and for the oxygen science that we were doing those. And the only way to read these really was to roll them down a very, very long corridor so you could see what the patterns were. You could see as each raster scan came through, and you could see the Lyman alpha and you could see the oxygen. So anyway, that was without the computing that we later had. So, yeah, is that enough for now, Kara?
Okay. Thank you.
I worked on many other missions later.
We'll cover
I
that,
worked
too.
after the geophysical observatories. I did work on one of the solar observatories, and then the Mariners, the Voyagers, and on. But that
Pioneer
was later.
Venus. A little bit of Pioneer Venus.
Yes. Oh, very definitely. Ian, forgive me. Yes. Yes.
Thanks, Sabina. Karen?
Well, I'm one of these people who started at the bottom and worked my way up. I started as a undergraduate student working for Bill Rentz, hand plotting on graph paper, which I brought some along just in case any of you don't remember what graph paper was.
And that's a slide rule? It's big.
I didn't bring my slide rule,
Okay.
but I did bring the Gerber scale. Did that, and then I went to work on the biaxial pointing controls. And so I have a rocket biaxial pointing control notebook. Then I went to work on the PDP-8. So I was after Gene McCullough and before Dave Stern, and we were working on this, what was to become the editor. And so I have some of PDP-8 manuals, and I have one of the programs, Dave, and the paper tapes that we used to store our programs on in those days. And then later on, we had mag tape. So from there, then, I started working for Charlie Hort, doing a three-dimensional radiative transfer program. And along came Barth, and Bill Fasty came from Johns Hopkins?
Hopkins, yeah.
And brought with him Mariner Venus data. And they were anxious, because I'd been working on the CDC 6400 by that time, I knew how to make plots and how to do stuff on the 6400, so we could read that tape on the 6400. And they were livid that I was not available over the weekend. And it turned out I was off getting married.
So you were allowed to get married?
I greeted Karen. Where are you, Karen?
Took a Saturday off?
Right. But anyway, so from Mariner Venus, then I worked on Mariner 6 and 7. Again, doing plots. I brought a CalComp plot from the 6400 from that period. Some Lyman Alpha Fortran in the notebook. From there, then Mariner 9. We did a lot of work on Mariner 9. And I was working my way up at this point on Voyager. I ended up being the operations manager. And then that lasted from 1977 to 1989. And in 1989, we launched Galileo. And for Galileo, I was the experiment manager for the UVS and EUV instruments. And when Galileo was then put into Jupiter to burn it up so that it didn't contaminate anything, I became an archivist. So I went on zero appointment and started collecting all of this old data that we had that hadn't ever gotten into the archive. So there was Mariner 6 and 7, there was Mariner 9, there was Pioneer Venus, there was Voyager, there was just all this stuff to be collected. And a good deal of it got into the archive, but there's still some out there I need to work on. So 50 years later, as of this April, I'm still hanging in there.
Congratulations. Yes, and Karen just did celebrate her 50th year LASP. Quite an achievement. Thank you all again for being here. Just wanted to, forgot to mention the format is we're going to have probably another hour of discussion and then give the audience time to ask questions at the end. We'll probably have a half hour or so of questions. So with that, you kind of started, Sabine and Karen, talking about what Dr. Barth brought here from JPL and the OGO 2, OGO 4, and then maybe you can talk more about the transition from analog to digital, because that came about the same time, right?
A little bit later.
A little bit later.
Right, well, Ken Kelly apologizes, he's got the flu right now, so he couldn't come. But he did give me some information. He came with Charles Barth from JPL, and Gene McNutt, who was later one of our engineers, he actually came from one of the contract organizations that were building the instruments for JPL. Ken and Barth brought the OGO 2 and OGO 4 and the Mariner 5 instruments from JPL, and they were calibrated at JPL, and they were analog instruments. So they output strip charts. And even JPL wasn't able to deal with it. He told me, he said they had a big computer, but there was nothing that interfaced these instruments with real products. So apparently Barth had some fair amount of conversations between Goddard and JPL and other instrument scientists discussing whether they should get into this computer age. And I'm not exactly sure, I didn't have a chance to ask him about it. But what Ken remembers was that it was shortly afterward from them coming that the PDP showed up. And I think maybe Phil may have some information about exactly when that PDP showed up.
I looked in my inventory of old equipment that I purchased, and as far back as I could go, but I didn't have anything on the PDP-8.
Yeah, we know that Gene McCullough was working on it in '67 and into '68, because when he left, I started working on the PDP-8 software. And then I quickly went to work for Charlie Hord and working on the big machine, and so the 6400. So, I'm thinking and we know in that publication by Gene McCullough that Jeff Pierce, who also he was a graduate student of Barth's, and he came from JPL with Barth. And he was involved with a lot of the hardware and engineering to get those systems up and running and talking to the calibration vacuum chamber downstairs. So that too was in like the 66, 67 time frame.
Yeah, so we should probably clarify that when most of us came to this university, there was the computer. This Control Data Corporation 6400, which was located a little bit to the and that serviced literally the entire campus. And there were probably a fair amount of time when there was nothing else on campus that you could call a computer.
No, I have to correct you, Randy. There was an IBM in the physics department.
There were a few IBMs. These were very primitive devices.
Well,
These were
that was true.
They were literally plugboard programmed. So in terms of actually, standard programming methods, that was the only computer that was around. And then LASP and probably the psychology department got some very early PDP computers. These were made by Digital Equipment Corporation, and they were the thing because they were something that you could put in your own laboratory, and you didn't necessarily have to go down to the computing center. As David said, we all computed with Windows while Bill Gates was still in junior high school, because you shoved your cards through the window, they ran a job, and then an hour later they shoved all this paper back out the window, and that was the way that things worked. So having your own computer and being able to do anything more or less immediately was just an incredible improvement. And
I think I remember when I came to LASP that the last computer bill was $20,000 a month. Doesn't that sound about right, Ian?
Probably about right. Yeah.
And that was a big incentive to get your own iron.
And that was what year?
69. So you, by a factor of 5, probably today at least.
Yeah.
I'll go back a little bit further, because before we had these larger computers, we had either slide rules or logarithm tables, and I very well remember looking up to 13 decimal places, values of pi, calculating them, doing modeling for atmospheres. And one day a Wang appeared. on my desk. There were, out of one box of a Wang, there were wires that went down the hallway, and a Wang appeared, and it had pi, and you could do all kinds of things that you no longer needed the log tables for. And I threw out all of the paperwork with the log tables in that pit. And during the Pioneer Venus meetings that were on campus here, I can remember there were some people from Washington who had come to look at some of the data that we had, and they spent a lot of the time playing with the Wang because they liked it too. That was 67.
Yeah, but we should point out that these were essentially just 4-function calculators for the most part, but they were an incredible innovation.
Yes.
And
They were desktop versions.
They were big.
Well, there was one box that was in the basement.
Right.
Yeah.
And cables ran it. They had like 4 terminals, right? And Dr.
Yep,
Barth
there were
got
4
one.
of them.
Yeah.
Did you get one, Ian? I don't know.
Yes.
I remember using one, I probably did.
And eventually there were 8. Yeah.
There were 8?
Yeah.
Okay.
Yeah.
The other thing we should point out is that everything we're talking about today that we call a computer had the computer horsepower orders of magnitude less than the forthcoming Apple Watch will have.
Or less than your way less than your washing machine.
And I'll go even further. I am very deaf, and I have an implant, and I like to tell students that this little computer right here, just this top part, can do more than any of the spacecraft that I worked on. So in my lifetime, going from paper and logarithm tables to being able to hear is a huge thing that's happened just in my lifetime.
Well, let me just interrupt about personal computers. That even the computers weren't personal. They were Pioneer Venus or Voyager computers, but you couldn't be so restrictive because there were so few of them. There would be Pioneer Venus priority computers, so you couldn't use them unless there weren't any Pioneer Venus people ahead of you in line.
So I think the real genius of LASP started with computers started in for the Mariner 1971 mission, the Mariner, what was to be Mariner 8 and 9. 8 never made it, so it was Mariner 9 alone. And that became the Mariner 9 spectral editing system, which I maintain today was still a major leap forward, not just at LASP, but in general in space science, in terms of what it was able to do.
Yeah, there's a lot of hardware new stuff that came in. Let's get Phil to talk about all of that hardware then that came in with Mariner 9.
Yeah, because when I started, we had the PDP-8, and Mariner was launched and on its way, but we didn't have anything really set up to analyze the data yet. We had to put all that together. And we set up 2 terminals across the hall in another room. Each of them had their own PDP-8E, small box computer, and a XY display, grayscale. It wasn't even grayscale, it was just on
It
and
was an
off.
oscilloscope for a while, wasn't it?
Yeah.
Well, they were really,
That was in the computer room, but in the operations room.
but those displays are really oscilloscopes in a sense too.
Yeah,
They
were
Yeah.
They could just do
dressed up a
dots. They
little
only could do a single dot at a time.
bit. Yeah.
Yeah, you could only do one line. If there was a dot, then that was it. So you had, in essence, one line.
Right, and that was the spectra, which is what the kind of data we had was.
You programmed
Right, teletypes?
the PDP-8Es had A to D converters. I mean D to A converters, 2 D to A converters, and you'd set the X value and then you set the Y value and say make it bright. And you could do about 1,200 points before it started to flicker. Because if you tried to do more, it would just...
Yeah, and in front of each of those displays was a teletype.
Dave, hold up one of those books with the pictures on it, right in front of you.
Well,
And the
Here's the
user
PDP-8.
could type in commands and then see the result on the
yeah, you can come look at this
display.
later. But
And the teletype and the computer that did display were interfaced back to the PDP-8 through just serial terminal lines, running at a whole 9600 baud, which was extremely fast at the time. And the other thing then we got was another, it was like an 8E, but it was called an 8I, because it was more integrated.
Yeah.
DEC was into E's and I's long before the rest of the world. And We got that because DEC developed a modem interface that you could interface to get high-speed serial data, again, 9600 baud, bits per second.
It's 48?
Oh, was
looked it up.
48? Okay.
Yeah.
From JPL. But then you had, the interface was in this newer box, and you had the PDP-8, which had the software, so we had to interface those two together. And that was one of the things that I thought was very interesting, because we actually made it so they looked like they had a shared memory. Data would come in over the serial line, PDP-8I would dump it into the PDP-8 memory, and then the PDP-8 would process it.
Well, and I need to interject just briefly that the other thing that Ken Kelly told me was that once he got here, all of the rest of the instruments that were done here had the, what did they call it? Sorry, I'm not an engineer.
They were digital?
Yeah, it became digital.
They used pulse width modulation,
There you go. There you go. So
which
all
was
of the
really an
instruments-
advance for those days, I think, because
Right.
I remember when I came, they had FM,
Prototypes?
they had,
Yeah,
Yeah.
yeah.
yeah, that's the analysis room. That's
How
Ian
about the
right there.
software that went along with the PDCs? Can you talk a little bit more about the software that went into the PDC-8?
The PDP-8?
There's
Yeah.
the displays, the tall type.
Yeah, that was the operations room for
For
Mariner.
999.
Yeah.
Two terminals. So it was
And
a
later for OSO too,
two-user
wasn't it?
system.
For
Was it
OSO
card
also?
readers?
Yeah,
Several.
yeah.
We had different computer for them. They were
Yeah.
PDP-11.
Well, that's Mariner data up there.
Yeah, so there were sort of two real major innovations besides just the hardware itself. One was that all of that was hooked up to JPL by a high-speed data line, high-speed being 4,800 bits per second.
Actually, there were two data
There were
lines.
two lines. Each of them had a box that was about this wide by this high by this deep, and each of them came with a AT&T engineer to keep it running throughout the mission. I mean, they were as much a fixture as any of us were in that room. But you have to remember that back in the olden days, as Sabine was saying, you know, maybe you had to go there to get the data or wait for tapes to come through the mail. Could be literally weeks or even months. But with this system, we were able to get the data in hours. In fact, typically what we would do is overnight, the data that were collected during the previous roughly 24 hours would be transferred overnight and available to the scientists the next morning. And again, you know, that probably had never been done before. That kind of remote analysis had probably never been done before. So that was a key innovation. And then the language aspect, which Dave did, was one of the other real major innovations there.
Thank you.
Well, we skipped for just a minute one of the things that Sabina did for Mariner 6 and 7. And that
Traveling back and
was
forth?
that she went to JPL, got the tape with the data, got on an airplane, carried it back to LASP.
Right.
Overnight, we cranked on it with the early system, and then she took the plots back to JPL on another airplane.
Yes.
And I don't know how many times you did that.
I don't know, and because they had to be shown at JPL in the
At the press conferences,
in
yeah.
the reports to the general public, and you wanted to have the data in a presentable form and not just a quick flash. So there was a special way of making multiple photos so your eye could perceive the data as it was running through. So instead of being, tell me how many fractions of a second it was and how many seconds you need to be able to recognize if you're
Yeah,
looking at a whole graph.
10
And that was
seconds.
the whole point of this
Yeah.
process.
Yeah.
And the only way to do it was to fly it from JPL to pick it up at the airport, process it, and then fly it back out again. Yeah.
No Federal Express back then.
Sabina Express,
I
yeah.
recall something about a Learjet. Does anyone remember that?
The Learjet?
To fly data? Don't remember.
Sabine, how did you get back and forth
Oh,
with flying back and forth? Did you,
Oh.
was it commercial or did you have this chartered flight?
Maybe the data tape
I
came on a
don't
plane.
remember because I know on the flights to the control center in Washington, those were commercial flights. But I've forgotten the JPL, I'm sorry.
JPL did fly the tapes from Goldstone to JPL, but I don't remember
I
flying them
don't
here.
know. I think it must have been commercial.
Yeah.
So much for my memory.
We've had a little time to think about it.
we were doing-
You know, you'll remember tonight, but don't call us.
So again, I don't think you can underestimate how radical it was to be able to sit down with Dave's software and actually manipulate the data directly instead of having to do the windows back and forth. I mean, you know, we're used today sitting down at a terminal making dozens of mistakes in a matter of minutes before we hit upon the appropriate method to use. But when you had hours turnaround, that was much more difficult. And of course, what Dave made possible was the ability to really get there and get personal with your data. It was an incredible improvement.
Scientists loved it.
Those are the wings. Those are the wings.
Well, there's the Wangs, yeah.
Yes, there are the wings.
There's
yes.
that's the
CDC.
CDC 64 over there, which essentially took up an entire floor of a building.
The big building.
A big building, yeah.
But when we did the other 8, we went a step further in the 8 because then the data was processed in real time. Every contact, we downloaded the data, received
Yes.
in real time here, process it, and
Yes.
turn around with the spacecraft correcting,
Yes.
pointing issues and so
Yes.
forth with the spacecraft, with those
Yeah.
spacecraft.
Yeah. In
I
fact,
think that's the first instance of
Yeah.
really interactive open loop control of an instrument,
Yeah.
of 2 instruments. in
yeah,
fact.
so let's make it clear. You actually commanded that instrument in real time
Yeah.
from...
Well, it was a 96-minute delay.
Was it that long?
Version of real time.
Went to the next pass, to the next
To
pass.
the next pass, okay.
But
Real
we did
time has
that.
gotten faster, Randy.
So at the
That's still
same time
pretty
you're
good.
doing Mariner 6 and 7, you were also doing OGO 5 and 6,
Mariner Venus, yeah.
and you were sharing hardware, people, resources.
Yeah, we were all sitting in that room, and actually, I was sitting behind that corkboard panel on my own teletype, doing Fortran and some remote GE system whose name I can't even remember.
But there was an even more primitive system. There was a teletype that would print out 21-word pairs, and it only sampled, Ken would remember, we had 3 photometers on there, and it could sample in the different channels. And Bill Fasty would call out the pair of numbers, and we would be sitting plotting with colored pencils, because that was faster than doing it, because we could almost do it in real time that way. And you know, then later on we'd be able to look at the data very fast, but strictly off using color pencils on a graph.
Yeah. Yeah, it was really busy and really exciting because there were so many different things going on at the same time. We had flybys, we had orbiters, we had solar things. Stuff was just going like mad. Well, and you look at this timeline, the same thing is true now at the time frame that we're in right now. So many things going on at once.
A lot more people now.
Well, that's true. And we're a little grayer because of it, right?
And we download data little at higher rate.
Yeah.
Also.
Yeah.
So one story I can tell you about Mariner 71 data processing, when Mariner 9 got to Mars, Mars was in the midst of it. Oh, yeah. Well, there's a story behind that, too.
We're waiting to hear it.
Okay. Well, anyway, Mariner 9 got to Mars. It was the midst of a dust storm, and essentially nothing was visible. And slowly, stuff started to emerge out of the dust. And one of the things that the UV instrument was able to do was chart the terrain height by essentially looking down and, if you would, counting up the atoms.
Right there.
Counting up
Yes.
counting up the atoms.
We produced the first atlas,
Right.
topographic
Right.
atlas.
So Karen was working on one of those terminals one day, and she was working on an overflight of Olympus Mons. And so she was working out the first really good altitude profile of Olympus Mons. So she did it, and I said, okay, Karen, what's the answer? And she said, it's 16 miles high. And I laughed, and I said, better do that again.
16 kilometers high.
No, 16 miles.
Yeah.
Yeah.
Yeah. So,
You weren't the only one that laughed.
yeah,
Laughter throughout JPL.
yeah, right. So it really.
But it's never been corrected. We still stand,
No, it's true.
Yeah.
yeah,
It's been confirmed by spectroscopic observations.
yeah.
So, yeah, so those were very interesting times, because literally everything we were seeing, no one had seen before.
Right.
Yeah,
The story behind that was that
Right.
I contributed, so we could get the data very quickly from JPL, but we weren't able to get the orbit and attitude information that we needed. So every day, Lonnie Lane would call me up on the telephone and convey by an incredibly primitive fax machine the numbers I needed to run the entire orbit solution here, and then we could combine that with the data. Initially, I did do that on the PDP, on the CDC 6400, but even that was too slow. So I got a terminal, and I hooked it up to a computer in Denver that was operated by the Denver and Rio Grande Railroad, and they sold their spare cycles to other people. And so I would run the orbit solutions for Mariner 71 on that computer, and then have them available very quickly. And I even worked on weekends, because we had a 20-pound portable terminal called an executive port, and I would cart that across campus to my home on the hill and do my work there and bring it back.
And Randy, you were a student then?
So then I was a student, yeah.
yeah. Well, in the picture that Randy was standing in front of there, the way we got images from the camera on Mariner 9, and they were generous in sharing them with us. And so we would mount these images on the back bulletin board, and then we'd calculate what the altitude was, and then Lynn Teets would go make plastic copies of what the topography looked like.
Cutouts.
Cutting them out with a bandsaw.
Right,
We
and
do
we'd-
Calcom plots.
Plexiglass.
And we'd stick them onto these pictures out in the back hallway.
They keep falling off.
Yeah, and I think, one of the funny things, I was looking for them last night, but up at my cabin, we had a fire, and while I was cleaning up, I'm raking, what is this funny thing in here? And here's one of these plastic topographies.
You have one of those?
And I have 3 of them now.
Oh, boy. You definitely need to provide those to the LASP archive.
It goes, okay, I agree. Okay,
Primitive but effective.
right, so the ozone discoveries on Mariner 9 on Mars, and the topography were some of the great science that we did with Mariner 9. And really a good deal of it had to do with how this computer setup was set up by Phil, and the software that Dave had written. And by that time, no, you weren't here until OSO, right, Margie?
Right.
Somebody talk about OSO a little bit?
Yeah, so let's go on and talk about OSO.
So I just wanted to say something about the visualization. So what you did is, and all we've been talking about, is turning the raw numbers from the data onto some memory form into some sort of visualization. And in your case, you had the pictures, the photographs, which were visualization, and then the altitudes calculated from this pressure method that were also visual and pointed right out of the wall on top of the black and white photographs. And the connection there is this is the same thing that happened with Dave's programs, is you were allowed to look at the data, visualize it, and the key thing for me was then visualize the model on top of the data. And as Randy said, what you would do in days and weeks, fiddle with one parameter, take that over a box of cards, and then get the output and plot the data yourself over the model. You could do there right at the Pioneer Venus or Voyager computer, you could plot the model and the data. Oh, it doesn't work. We got to shift by 10 seconds, or we've got to add more ozone, or we've got to do, maybe the spacecraft wasn't looking quite at the position it was, change one of the geometric parameters, and you could play with the data, interact with the data, and the models at the same time. The computer treated them the same way. And it was, I think, an extension, a natural extension of what was on the black wall with that pink plexiglass
Yeah.
and the black and white
So
photos.
this technique of data visualization, was this created at LASP?
Yeah, it was something that Barth was just adamant about. I mean, if you, as a side note, before any student or professor went to the AGU meeting, you had to go into a room like this with Barth sitting there, and you did your presentation, and if he couldn't read your plot from where he was, back you went. You had to have it simple, you had to have it direct, so that anybody within 1 minute could read what was on that plot. He was a real adamant about visualization. And it's one of the things that drove an awful lot of the stuff that we created, and the way we created it.
So I think that brings us to probably Mariner 9, and if you can talk about some of the changes.
That was Mariner
This was
9.
mostly Mariner 9, also.
Okay.
Also now.
OSO.
OSO.
Yeah.
Also,
OSO.
well,
I thought also.
I work on also, Margie was there, Dave was there, Phil, Ellen Hansen, basically she was also the head of the OSO 8
And
operation.
Marilyn or Elmo?
Elmo Brunner was the PI for the last instrument, and Roger Maurice Bonnet was the PI for the French instrument. We brought the French team here. Well, I was part, that's why I came here.
You were the French connection.
I was a French connection, yes, but a nice one.
Yes.
On the other spacecraft, the two main instruments were the pointed instrument, and they were co-aligned. So we had to share the pointing between LASP and the French instrument. So we decided the easiest way to do that was to bring the team here. So we had all our PI and COI and our guest investigator at LASP doing the planning for the instrument, and on a daily basis. For the first year and a half, if I recall correctly, the pointing was shared. One day was the French instrument, the next day was the LASP instrument, and so forth. We switched that after 1 year and a half to a weekly pointing, where one instrument will have a week of pointing, the other will have another week of pointing, and then we went to 2 weeks by the end of the mission. But we had to do something like that to bring the team here because there was no Skype, no WebEx at the time. We could not collaborate on a project where we wanted to be very interactive with our spacecraft. The way the system was built, we had 2 lines to the Goddard Space Flight Center, to the Mission Operations Center. They were 7.2 kilobits, if I recall. Those 2 lines. One, we were receiving real-time data, 16 times a day, where we could analyze the data and decide if we needed to do some correction to the pointing or to the instrument setup, generate those updates, ship that via a telecopier machine to Goddard, where they will uplink those updates that we wanted to do and fix our pointing, for example, or the instrument setup. We could also react to solar activity. We had a link, if I recall, from the NOAA, a real-time link where we could see the H-alpha image of the sun, and we were receiving calcium-2 image from Sacramento Peak daily, so we could analyze that and decide what was the plan for the next day. So the planning was done the day before execution. It was a whiteboard, if I recall, on which people will write orbit after orbit what they will do. We will generate the command, the French team, the US team, merge those commands, send that to the Goddard. There will be uplink for the next day, and we will then react in real time to what was happening. So we had an open loop type of control we did.
And
we
this was
did that.
science going on,
Yeah,
24
science
hours
going on.
a day.
That was possible because of the system that Alain and I built, well, and I, Margie, Phil, and so forth. We were also doing some visualization in real time of the instrument status. Phil built those boxes where we didn't have a software like OASIS to decommutate the data and visualize that. Phil built some hardware decommutator where we could see when the real-time data came, we could see the status of the instrument, what the instrument was doing. Remember that?
Just a bunch of little LEDs.
LED,
that light up
we are doing that.
whenever
And
the right
so
thing's going on.
it was a step forward what was done before. We had real-time data and open-loop control of the instrument and the spacecraft.
The bigger step, I think, was with, again, data visualization.
Yeah, that's
Since the French were coming over to work with us, we bought identical systems, and they brought theirs over, and they were sitting in the same room facing each other. And I had built a early image display system, monochrome but grayscale, and it was probably like 120 by 128 or something. And got that working. The French were developing their own image system, and they did not get it working before they brought it over here.
Probably true.
So I had a lot of fun with that. They sent the schematics for it, and all the signal names on all the prints and everything were in French, so I had to have it translated for me to figure out how it was supposed to be working. And I don't know, it took me several weeks, but I did get it going for the mission, and so they had grayscale image
For the
visualization also.
You know,
Yeah.
and one of the things that I saw in that manual that you sent around, Alan, was some engineering monitoring, which I don't think we had done very much of before that.
The engine monitoring was done by the box that Phil built.
And that little display that
Display,
you
we could
built,
see
right?
the health, every real-time passes, we could see the health and the status of the instrument, what the instrument was doing also and so forth. So it's not what we do now, but it's the first step. It was
Yeah,
hard-coded.
yeah, first time.
There is another thing, two things I want to say on OSO8. To be able to do this turnaround, you have to have some tool, and the tool, the Sol language was the tool that we had to visualize our data almost in real time. 10 minutes after the fact, we could see what was going on and could correct them.
And Sol stood for
Solar or
Observatory language, or
something like that.
solar observation language, or
And that was,
something like that.
So
I found on my archive,
Observing
the first page of the documentation signed by
Yeah, it was
Dave
up there.
and Margi of the Sol language in 1st November 1975.
So can you call out some of the differences between the spectral editor and SOL and IDL? What were the key differences?
Well, the big differences was that, starting with Sol, we had PDP-11s, which were 16-bit machines, and had a real instruction set where a PDP-8 was more like an abacus, I guess.
Yeah,
You know, it had 12-bit words and a 4,000-word memory bank, so that was pretty much it.
We had three of those.
Yeah, four. We had four.
12K altogether.
Oh, 3 memory banks on the
Yeah.
big PDP-8, yes. But, so those systems were based on simple commands, mnemonics, where A would stand for add on the very first PDP-8
Yeah.
system that
yeah.
McCullough did. And there were 16 commands. And so then when Mary came along, I made 2-letter commands. So you had AD instead of A for add. And it had more memory, so you could have more spectral registers. And then I made it programmable so that it would store the commands in a buffer, 1,000-character buffer, I think. And it would interpret them. So you could write little macro things.
Right.
So you could say, subtract this spectrum from this spectrum and divide it by this and plot the answer. And
Yeah, we couldn't do that before.
Yeah. So that was really basic. And then, starting with the PDP-11s with OSO, or with Sol, I'm sorry, these were actually real languages that had a real parser, and they had a real grammar, and they had subroutines, and
And it became popular outside of
Yeah.
LASP. I know they used it a lot at Goddard.
yeah. And
That's because we were transporting a lot of our
Yeah.
graduate students to Goddard and
No, that was-
Johns Hopkins and
it
lots
went,
of places.
I mean, everything spread like viruses.
Yeah.
In
No,
a good way, right?
Yeah, in a good way. And some scientists would come here, like Uwe Keller, and he would see what we were doing, and he'd bring it back to Germany, and and same in England.
In
Yeah.
France, the French used it.
Use it here, yes.
Yeah.
Jean-Claude
There's one thing I want to add on OSO8 is something that people forget about the LASP instrument. There was 1970, he had a computer on board, a 16-bit programmable computer. I think that's probably one of the first.
Junior.
Junior, yes. And they did closed loop control of the observation. And that's something that didn't exist before, I think.
That may well be.
16-bit computer on board, programmable. So we had closed loop on board for the LASP instrument, for the French and the LASP and the instrument open loop control with a very short time reaction time. And that was the first also, I think. And the fact that we had two teams together, so it was an international team here, working here also was something first also.
Well, I think the first two is that you were able to send commands to the spacecraft. Did they have to go through Goddard? Did they have to okay them and bless them? And
we did the daily load, the French and the US daily load. They were merged here, verified here. The load were command for the spacecraft computer memory at the time, the spacecraft command memory. They were sent to by one of those 7.2 kilobit line to Goddard, where they will merge them, probably French check them and so forth, uplink to the spacecraft. The correction we are doing in real time, quote unquote real time, where we will mark them on a piece of paper and telefax the piece of paper to the control center, where they will enter them on the next real time contact.
so they were actually sending the commands.
We never sent directly the command, but they never really check what we were doing. We were able to modify the memory of the spacecraft, those commands. They were doing what we told them to do.
But for the OGO 5,
Louder.
oh, I'm sorry, for the OGO 5, which the French also had an experiment on, this was a highly elliptical orbit circling the Earth, but going a third of the way to the moon. And the French went to Goddard, and I went also. We turned the spacecraft over so we could look at a comet. And that we had to do through Goddard. We couldn't do it from here. We had to be in Goddard with, I think Bonnet was the one who was there at that time. And
So that was the next implementation of this.
Yeah.
Yeah.
But on the way, it was a daily basis.
Yeah. So, this is the progression of how things developed, and we said, well, why do we have to go to Goddard? We should be able to telefax this.
We were receiving also the playback of the orbit just after the fact for the first year over one of the 7.2 kilobit line. After that, after 1 year, I think the dump were done at night, the transfer were done at night. But we were able to see the data right away.
How about talking a little bit about Voyager 1 and 2?
Could I add a comment?
Yeah.
Sure.
OSO 8 from Gary Rodman?
Yeah.
Because I saw him yesterday. He's on a plane to Hawaii, otherwise he probably would be here. But I think it was an OSO 8 story. He said that they got an HP calculator. I believe he said it was an OSO 8 project. Y'all could probably clarify that or not. And it was so revolutionary to not have a calculator you could have in your hand versus attached to wires. And that people were wasting their time just playing with it, like we waste our time with iPhones now. And then at the end of the contract, you have to put up all your stuff for the government to reclaim. And we had apparently LASP had all this expensive machine shop stuff they had bought. The government didn't care about that. They took away that one HP calculator that LASP had.
I can tell you that the PI, the French instrument, Roger Maurice Bonnet, used to work with some Russian and will bring HP calculator to Russia to make friends. So that was the gift, because they didn't have access to that.
Wow.
Should also point out that one of the real advantages of the French team on OSO was that every celebration they brought a box of champagne.
And cheese.
Yeah.
So if you went back to the old LASP building on campus and you go into the conference room and you look at the ceiling, you would find bunches of weird dents. Those were caused by popping champagne corks.
Yeah.
I will add another advantage to have the French team on board is when the NASA tried to cancel OSO 8, the French embassy went on the horn and they told them they could not do that. We had spent enough money already.
Well, one more thing that I remember in particular, because I wasn't working on OSO, but they would periodically have these solar workshops, and they get all of the PIs and co-Is together, and they would talk about what they were finding and speculate about, well, what does this mean, and where does that solar flare come in? How come it's got two ends, and all of this stuff? Wow, this was really great. And I don't remember how often that happened, but it was just really real-time science was going on. And it was exciting.
Of course, that's not SDO and so forth. That's pre-SDO.
Right. Well,
So
and
how-
similar to what you were saying about the HP calculator, in the Voyager days, which we're sort of transitioning into at the
yes,
moment,
please.
I was asked to do an interview on NPR, and the guy on the other end, he says, well, I'm looking at my calculator. How does this compare to what you've got on your spacecraft? And I said, well, there's something like 1,048-bit words on my spacecraft, and we're able to do all of this, and it's a heck of a lot less than what your calculator's got. Yeah, but Voyager 2 launched first in '77, and Voyager 1 launched in September, about 2-3 weeks later of '77. And we were, the PI at that time, Chuck Lilly, was fascinated with stellar, not only calibration, but understanding how stars were varying. And was looking at a lot of stars with Voyager 1, and ended up overexposing the photomultiplier too. And so at that point, as opposed to being a simple programmer for Voyager, I became an operations manager. And it was then my job to go through all of the sequences, looking to see how much we were using the photomultipliers, looking at the engineering and the science data as it came back and saying, oh, well, that's too bright, we shouldn't have been doing this, or, you know, you're cut off. So I became the fall guy. But we ran, oh man, it was exciting. But these were, they were not orbiters, they were flybys. So everything had to be in the can and working right months before. And every time we had a gamma ray hit in one of the computers, something would go haywire, and the main computer wouldn't work, or instrument would start doing funny things, and so we'd have to turn it off and turn it back on again. And the photopolarimeter measured polarization of light, and it had a series of wheels inside. Larry remembers this very well because he did that ring data stuff. But we very quickly realized that if you turn the wheel and got one DN value for where the wheel was located, you got a slightly different answer than if the wheel didn't quite make it quite so far and you had a different DN value. And so my job ended up being a lot of this engineering checking. And I remember a big sign that I put on the wall when we got to Saturn, so that when Larry got off of the elevator, it said 161.
Right.
And that's the one we're calibrated on. So and we were all very happy about
That's
that.
digital location of the wheel.
Right, the digital location of the wheel. Voyager started out being called Mariner, Jupiter, Saturn. And it wasn't until Voyager 1 went past Saturn and got good data on Saturn that NASA decided that the second spacecraft could go on to Uranus and Neptune. So it was at that point that then it became Voyager as opposed to Mariner, Jupiter, Saturn. And we went by all of those planets and all of those moons. There's so many moons. Eventually I lost track. Larry named his
They're
two
like my
daughters
children.
after
But
them.
anyway, those two trajectories were called JST, the first one, with Jupiter, Saturn, Titan. And if we missed Titan on the first flyby, that was one of the mission requirements. The second one was called JSX, because if we didn't get Titan on Voyager 1, Voyager 2 would be redirected. And therefore, if it flew by Titan, it wouldn't be able to go any place else. Luckily, we've got Titan, and JSX became Voyager, which was Jupiter, Saturn, Uranus, and Neptune.
Yeah.
Can you talk a little bit about the hardware, software used on Voyager?
Well, the operations area was basically two computers, and I really don't know what they were at that point, but we had
They
two
were
students.
Vaxes.
Vaxes by then.
Vaxes.
Yeah, digital
The
equipment.
VAX machines.
Vaxes, those were probably the best machines that DEC ever made, as far as what we were using them for.
You're right, okay,
And
yeah,
of course, like you say, this was over several years, so we even had evolutions of those as we went.
right. And OSO was still using what had been the Mariner operations room, and so we were put in the other room next to it. We had two terminals, Pioneer Venus and Atmospheric Explorer had another terminal, and so there were a series of students who were getting these data over. By then we had these data lines, and they would pick up the data at night, and we had a computer student by the name of Ali Barami, who then eventually went to work for Dave. But Ali wrote a series of plotting programs that would work on the backs so that the students could sit there and make a Tektronix hard copy of the screen and put it into a notebook so that we could verify that the engineering was working, and we could see what the count levels were versus what the engineering was doing. And because there were these three wheels, aperture, analyzers, and filters, you had to be able to look at the engineering to figure out what the science data was telling you. Eventually we had to reload our what were called fixed pattern noise tables on the spacecraft so that we didn't step quite so fast. We realized after a while that because we were stepping through bright objects too quickly, the signals that we were getting were being corrupted by whatever bright thing that you saw in the wavelength just before it. So on Voyager, we had all of these canned sequences, which then called these fixed pattern noise tables in the spacecraft. And so when you wanted to change one of these, you had to go through a whole series of reviews. And but we made it. We made it.
I want to come back to the style of the flyby. This put a strain on both the hardware and the software, because each of these were the first ever flybys of those planets. You had to have, and everything happened within hours, the best data. You had to have everything set months ahead, and there was almost no real-time reaction, only in the case of some fault, the spacecraft went into a safe mode or sleep, that you could send a command. Otherwise, whatever you had months ahead of time was what happened that most critical period. And it's that sort of drove to a lot of checking. That period had, like Karen is just talking about, immense amounts of checking, both of the sequence and then of the data as it came in, because there really were no alternatives to that, no second chances. Well, in some cases there were two flybys of Jupiter and Saturn, but otherwise you never had a second.
Yeah, and we always had what was called a contingency plan sequence, quote, in the can, so that if something went wrong with the first one, if the onboard computers got hit with a high energy particle and turned anything off or whatever, you could load up the second sequence and then start running again.
And so you had to actually have several of these sequences. You had to have the nominal sequence and the backup sequence in the can, and then somebody would have to send a real-time
Right.
command to go
Yeah,
to
we
backup.
had lots of real-time command. I have piles of real-time commands to fix things. But one of the really exciting things that you remind me of, Larry was a graduate student during all of this.
Until I came here. then I met Dave Stern and Charles Braddock.
Right. We went past Jupiter, and Charlie Hart had been out there, and we'd been having trouble with one of our instruments getting these wheels to work right. And I got this call at about 4 o'clock in the afternoon, and they said, "Where's Charlie? We need Charlie to come back. We need to turn the instrument back on." I said, "Oh my God, where's Charlie?" So I started calling the airport, And Charlie was just about, Charlie Hord, the PI at that time, my boss, was about to get on an airplane to come home because he was beat, he was tired, we'd been working like mad to try to get these things working. And I said, Charlie, I'm sorry, but you got to go back to JPL. I said, the project director called me and said, you got to come back. And so Charlie said, well, I don't know. And when I was talking to, and let's see, it might have been Parks. I can't remember exactly who it was at that point, but I said, if you want me to tell Charlie Hort to get off of that plane and come back to JPL, you got to give me a good reason. And he said, we think we have discovered volcanoes on Io. And they wanted us to turn on our instrument because we would be able to see those signals. And so back Charlie went. Charlie Barth went out to Louise and got a suitcase of new clothes, and he went to the bank and got more money, and all of that went out to Charlie, and we got the instrument going again. But by that time, then the spacecraft was too far away, and we couldn't turn around and look at it. But all of these exciting things went on.
So in our last few minutes, I'd like to spend some time on a mission that changed LASP significantly, I think, and that's the Solar Mesosphere Explorer.
Yeah.
A lot of the work you guys put into this beforehand kind of led up to that, our capabilities in that. So,
Yeah.
Randy,
Randy,
let's start with talking about SME a little bit.
Yeah, so I think everybody probably knows the origin story of SME. It's certainly a part of the LASP lore, how Charlie Barth harangued NASA, particularly Noel Henners, until finally they gave in and allowed this anomalous small Explorer mission to actually take shape, where the university would be essentially in charge. Charlie was the PI for the entire mission. There was a bid for building the spacecraft, and thankfully Ball Aerospace won, so it became a pretty much all Boulder type of project. And one of the things that was in the original proposal for SME was that we would operate the entire spacecraft. I talked to Barth a couple years ago about this, as to where that came from, who decided that, and we weren't quite sure. He didn't remember putting it in there. Alain Hansen, who had been the overall manager of operations for the last part of OSO 8, probably was very clear that we could do it, and she might have convinced him to put it in. But anyway, when we actually got the contract, and then we said that we were actually going to do it, there was quite a bit of hemming and hawing on the part of NASA. Could a university actually operate an entire spacecraft? And essentially, for the most part, they took the stance of, okay, let them try, and when they fail, we'll pick up the pieces and we'll operate it from Goddard like we always did. So Alain was put in charge of the operation system for SME. I was probably the second person. I was probably the second person hired for operations, and my job was essentially to wrangle all the software bits. But we knew that there was one key part that we had to do before all others, and that is we had to actually sort of scale up, if you would, our operational capabilities, which were good enough to operate, for example, a single instrument at a time, so that we could operate an entire spacecraft at a time. So she and I went around, and we went to every place where NASA operated spacecraft. We went to JPL and looked at how they operated planetary spacecraft. That didn't fit at all with what we wanted to do. We went to Goddard. We went down to Houston, looked at how they operated manned spacecraft. That definitely did not fit with the notion of a small Explorer. But Goddard was actually pretty good. They had a system there where two people, in essence, could operate a spacecraft. And that was exactly the right number for us. We knew that one person was not the right number, because then it would be either a professional or a student, and neither of them, the second was not something that we wanted. We wanted to be sure that we I guess the first one is something we didn't want. We did not want just professionals operating the spacecraft. We wanted student involvement. But we knew that we couldn't talk NASA into having solely student operations. So the obvious answer was two. We needed a professional and a student there to operate the spacecraft. And the Goddard system fit that pretty well. And it turned out that they were just rebuilding that system. They were having Westinghouse Aerospace redo that system for them. Yeah, so that's the original operations center there. And so they agreed that we could have that software. And in fact, for the final handover of the software, I flew to Baltimore, to the to the Westinghouse Defense Plant, and was there when they gave the final presentation. But then they had to mail it to Goddard so that it went through the proper channels. They just handed me the tape. So I had that software before anybody else did. I flew back on a Friday night. Saturday, I ran it through the computer, and I was just aghast because there were all sorts of obvious mistakes and problems. And it wouldn't fit in the small PDP 1134 computers we had. The ones that Goddard had were about 3 times larger. So we scratched our heads and decided we were going to have to completely rewrite this software. So we delved into it quickly. Marta Barthuli, who's here from Ball, she was Ball's key software liaison and integration and test, and so she pitched in and helped, and over a short period of time we were able to essentially rewrite that software completely so that it would fit in our small little computer. We used it throughout the integration and test phase. Both Ball ran it for spacecraft integration, we ran it for instrument integration, then we were able to run the exact same software for integration and testing, and then the same exact software on on-orbit operations. Very, very powerful capability. Even though Goddard had used that software for operating, even they did not use it for their own integration and test. So it was a very unique situation where we were able to use the exact same software throughout the entire process, from individual instruments to full-up integration to launch operations and on-orbit operations. That system augmented by other software to do key functions like orbit and attitude calculations and planning, was an extraordinarily successful system, and we ran for almost 7.5 years of actual operation with that software, and it all worked very, very well. But the key part, of course, of the whole thing, I think everybody who was involved in SME, was the student involvement. We had about 15 or 16 students at a time, I think. And over the course of the mission, that added up to almost 100 different students. So many students got their start doing SME operations. Chris Pankratz, Chris is here. He started out as an SME student. Guy Butelschie's, who was the Lockheed Martin project manager for Maven, started out as a SME student. Some of the professionals that were here then are here now. Dave Welsh, for example.
Jack Faber.
A couple
Jack
of,
Faber. Yeah.
One of Barth's children told me that he worked
He did.
as an operations person.
He might have. So Jack Barth worked with me in some of that early software development.
Okay.
But he did not work as an operator. But
Okay.
it's possible that one of the other Barth children did. I don't remember.
Was it Matt that worked for me for a while?
Matt worked for you.
Remember that.
That leaves Rob. I don't know if
No, he didn't.
he did not. Okay. So yeah, so
But
Jack.
Mary worked for me
Yeah,
during
Mary
Mariner.
worked here. I think every Barth kid worked at LASP at one point or another. That's for sure.
Randy, can you talk about how you recruited, hired students, decided how they would
Yeah.
fit in?
Yeah, so again, I think Alain was the real driving force in putting together the basic plan on how we would do the student involvement. One of the early decisions, and something that we've kept, I think, to this day, is that we did not require someone to be in a technical or scientific area. And so we had people from all sorts of different areas. We had art students, history students, music. So we would put out ads towards the end of every spring semester, and then we would take applications, we would do initial interviews, and ultimately select N number, however many we needed to fill out the class, depending on how many people were graduating. Jack Faber, I think then as now, took on a key role in educating all those new students as they came in. The education program was extremely rigorous. We essentially ran them through a summer-long program where they were here 40 hours a week. They learned everything there was about how that satellite was operated and how it worked. Nobody was a specialist, if you would. Everybody was a generalist who could perform a wide variety of tasks, even though they might ultimately end up in a special area. Everyone was trained as a generalist. They had to be able to demonstrate their abilities through tests and on-console operations with other people looking over their shoulders. So that was exactly the same model that we used when we were able to reinstitute operations with Snowy and future missions after that. We modeled that completely after the SME experience.
We still use that today.
And, yeah.
Yeah, our students were only obtaining the data, running canned programs, looking at it to make sure that everything looked okay. I mean, the programs that Ollie wrote for me allowed me to sign in from home. And so if one of the students saw something unusual, I could call the plot up from home and decide whether it was something that we needed to address right away or not. But we didn't have any students working hands-on on the spacecraft itself.
So with the students, I know we eventually evolved to more automation.
Yeah.
But initially with SME, there was no automation, is that right?
Well, in essence, it was roughly the same as it is now. In essence, we had the system that we used, the Goddard software that we had rebuilt, was not that different, if you would, structurally from OASIS. OASIS is far better in every respect, but the basic functionality was largely the same. So we could run canned procedures to do, particularly during the integration and testing. Ball would put together procedures that ran to thousands of lines of code so that it could run the same procedure over and over and over again, making sure that anything they did not disturb the overall capabilities.
And that language was called
STOL, Systems Test and Operations Language, and it was a Goddard invention. They had come up with the initial concept of this language. And again, just like with IDL, it was a very powerful part of the whole system because it allowed us to write these scripts and to script, I think, probably every spacecraft that you guys did at Ball before, the integration and test guys had to enter in everything they did and watch what happened and then enter something in and again watch. So this really automated and sped up that entire process and really helped in the reliability of it all.
Right.
But I think Bill's question was also in automation. Could you automate the contact in real time like we do right now?
So that we could not do. So we had, at least initially, we ran 24-hour operations for SME. Ultimately, we had to back off from that somewhat. But yeah, we had to have people there all the time. The NASA ground stations, which were about 6 or 8 different stations that were scattered around the world, gathered up the data, transferred it through Goddard, just went right through Goddard. They were a bent pipe, came right to Boulder, and then we could record those data, and similarly any commands went directly from here through Goddard as a router, in essence, to the station and then on up to the spacecraft as fast as the speed of light would take it, essentially. And so because of that, you had to be around whenever the spacecraft was active. It could be active any time of the day or night. Later on, when we did some of the other missions, we did a substantial amount of automation so that the passes did not have to be attended. The data would still roll in any time of the day or night, but the system could monitor and see if there were any issues. If so, then they would let us know, an operator on call at all times, and then we could do something about that.
That's the OASIS software.
That's the OASIS software.
But the initial setup
Yeah.
was students here 24/7, sleeping on the floor in between contacts.
I presume so, yeah.
Yeah, we worked a little bit different in that we had team members at JPL so that we could talk to them. JPL needed to have an instrument person available when any real-time commands were being sent for our instrument. And so we would teletype them, or email eventually to the people at JPL, who would then give it to the JPL authorities, but then stand by and look at the teletype as the result came out. But yeah, we handled it a slightly different way. But I also wanted to ask, now was that system also the system that Alain then took and was started to be used for remote processing of telescopes and?
No, that was OASIS.
Yeah. So what happened was that after SME, it became pretty clear that this was a very potent capability, not just for spacecraft operations, which is what it had been used at Goddard, but for instrument operations, instrument testing, and all that stuff. So we thought we could put together a version of that that could be portable enough and usable enough by scientists that they could do integration and testing with it. And so we pitched that to NASA, and they gave us a pittance of money to develop it, but we were able to show that it was a good idea, and over the years that then developed into what became OASIS. There was a substantial development effort to update that software, of which Margi played a key part, and Alain played a key part, and others as well. And OASIS was really a much improved, in almost every aspect, it was a much improved version of what we had for SME. And it could run on smaller stations like the first initial Sun workstations, which were coming out at about the same time.
The Microvax.
Yeah, so that really...
Vax to Unix, oh my God.
And Linux right now.
So that really allowed us to make a system that could be used for a lot of different things. So it became standard. There was one time when I maintained that more spacecraft were being operated with OASIS than any other specific piece of software, and I think that was true. That was in some of its early days when we had a number of different users. Ball used it extensively, and others as well.
Lockheed Martin.
Lockheed Martin used it, and
Telescope, some remote scientists that were using telescopes.
During tests, we tried to work on telescience quite a while, for a while with that, and we had one of the telescope at the Sommerbusch Observatory. We had control. I think, Jack, you worked on that, right? Yes. So with OASIS, but OASIS is still used right now. So all our spacecraft are controlled by OASIS here. So.
The other key technology that developed up then out of SME to today was the planning and scheduling software, which started out as a dedicated piece of software for SME, but Tom Sparn and others took that software and ran it through to a nice piece of software that was used on URs, an extremely important part of software for the UR's mission. And then later on, that became OASIS PS, planning and scheduling, versus CC, command and control. And those two pieces of software form the nucleus of a lot of our operations to this day.
A similar thing came out of the Voyager stuff that we were doing, in that when we wanted to plan a slightly different observation than what was in the can already, either a scientist had to go out to JPL and sit at their computer to design this with their software, or to transmit that to one of our assistants that was working out there, so he could sit down at their software and get the commands and the pointing correct. And when Galileo came along, I said, you know, this is nuts. We should be able to have our own scientists with our own software package sitting right here to do those observation plans. And so that was one of the things that went forward from Voyager into Galileo.
So sometimes SME is claimed to be the first spacecraft operated by a university. I would put an asterisk next to that claim. The University of Iowa operated a spacecraft called Hawkeye back in the mid-'60s, I think. And they actually did a little bit more than we did because they actually had the antenna there at Iowa that was used for communication with the spacecraft. But there were some significant differences, and key difference was that Hawkeye really had no command uplink per se. It was a fairly dumb spacecraft, so it just did its thing and the data rolled down at appropriate intervals. So in terms of doing what we would call spacecraft operations today, which means closing the loop between data coming down and instructions, commands going back up, SME probably was the first time that was ever done completely at a university.
But
The Hawkeye, that was James Van Allen.
was Alain. Yeah.
Yeah.
I know we're kind of running out of time, and I want to allow questions from the audience too, and we're kind of, we were going to allow another half hour for
3:30.
questions. But I wanted, Phil asked if he could do a quick presentation. Do you need a microphone?
So a lot of the history of LASP has been studying the sun and all of the planets in our solar system. And I'm sure, I hope all of you know that LASP is the only organization that has done that for all of the planets in the solar system. And even beyond that, Randy and I would like to present this. We're the only people who have worked on all of those missions. We just recently added Mark Langton. He wasn't at LASP when Mariner 9 flew by, but he did work on Maven, and so he was just recently added.
Wonderful. Thank you very much. Very impressive. So it's difficult to stop at this point in our history. We've got, many more missions, and I'm hoping we can bring all of you back to talk the rest of the story at some point. I'd like to.
About halfway there.
We're halfway there.
Yeah, but look at how many missions there are to do.
Yes. But I'd like to open up questions. Tom?
It's not so much this mission operations, but a little bit of history of LASP. So y'all didn't have the advantage of, and maybe you did see these slides because you helped put them together, but we got to see some of the history of LASP going past behind you. It was great to see many of you up there doing stuff. Some of you with more hair now, or more hair then.
Browner hair.
But
Grayer.
one of the things that I don't know if I ever heard a good answer is, when did LASP take on the name LASP? I know some of the old papers. LASP
When did LASP become
It used to be Upper Atmosphere Loud in the 40s.
Yeah.
Somewhere.
I think it was in 1965.
No, I can speak to that.
Oh, I can too.
Because Barth actually had me do research in that. So he asked that question to me just a bit before I retired. And he asked it of me because I sort of informally took care of the Rents archives for no good reason. They just ended up in my office at one point, and I kept them with me.
Do you have the strip charts and his original book of the Lyman Alpha in the 1950s? Somebody has it. I saved it, and it disappeared in one of the moves from one of the buildings to the other. And it's a book with Bill Rentz's handwriting of the original LASP.
So I do not remember that, but Tom has got everything now that I had, so you can check with me.
He said it's in a closet somewhere.
So anyway, what I discovered was a memo, and I even have it. I didn't bring it today.
No, we want you to get it right, because Charles is looking over your shoulder.
That was from 1963, where Rentz had written a letter to someone as the director of the Laboratory for Atmospheric and Space Physics. So we had always assumed that name was coincident with Barth arriving, the new building, that whole major transition of power, but in fact it was earlier, 63 at the latest.
Yeah, when I came here in 1954, Bill Renz was and the Upper Air Lab, it was called, that had the pointing controls that made it possible to send a rocket and to focus on a fixed object, so they could do some rocket observations, and that's how the very first
Biaxial
alpha
pointing
was done.
controls.
That was done in the beginning 50s, which is why I rescued Bill Rent. He put it out in the hallway, his original book with the original strip shot.
Yeah,
that would be great.
That was in the 50s.
Rentz had
And then
discovered
what-
Lyman alpha. Rentz had discovered Lyman alpha,
Yes.
or verified that it was there.
Yeah.
Yeah.
He and Pietenpol, who was head of the physics department at that time, had a rocket which was one of the surplus rockets left from the Second World War, under which I grew up under. So it was a big point for me that how useful these things could be. Anyway, at that time, the Upper Air Lab and a whole bunch of graduate students were then starting to become what later became Ball Brothers. A whole group of them that are still, some of them still here in town, that went over to Ball Brothers, and that the strong connection between the Upper Air Lab. And then in the beginning 60s, there was Ed, I should have looked up the name, from
Mackey?
No, he was from NASA, not NASA, it wasn't called NASA at that time, the National Science Foundation. And he, together with Bill Renz, put together the proposal to build a building so that it was no longer in the physics department. So that was in the beginning 60s.
Okay.
Yeah.
So it all comes together, we'll say 63, plus or minus a bit.
Yeah, and the dedication was 65. The new building had just opened. I remember I was there for that.
And the new building was
dedication.
called LASP.
The new building is now the old building.
Old one.
Occupied by mostly other people.
That's the Dwayne wing here.
That's the
Yes,
Dwayne wing.
yeah.
Yeah, when we,
When it was built, was it just one building by
Yes.
itself?
Yeah. There was a picture of it,
yeah, it was out in the middle of a sort of a dirt lot. All
It
by
was
itself.
where the tennis court used to be.
Right,
Yes.
and
There was cows and pigs roaming around.
No.
so the whole Dwayne complex, the Gamow Tower, the Gilla Towers, all those came later.
Yes,
So, yeah.
they were. We watched them the footings being poured.
Yeah, in fact, we couldn't avoid watching because it was happening all around us. It was often noisy.
Any, Jack?
Jack.
Yeah, I had a chance to have a few conversations with Fred Jouchoux. I'd love to hear any remembrances you guys have.
Remembrances of Fred.
Well, I actually worked on the biaxial pointing controls, and so I interacted with Fred off and on, but it was quite late in his career. But there was a section on the top of that Dwayne building where we tested the rockets. And so when the sun was out, we'd take one of the biaxial pointing controls up there and see if it would zero in on the sun and test all the electronics and all that. We were put out of action once the Gilla building was built, because the Gilla building was right in the way of the sun in the afternoon.
Kind of like the building next door here.
Yeah, right.
So,
But Fred went to every, what?
So we have to build a new building now.
Well, there you go.
so many of you probably never met Fred, but he was one of the stalwarts from the early days. He had been in the war and had done, just by happenstance, had been involved with looking at the German V-1s, I think, not the V-2s, but the V-1s, and sort of got into rocketry from that. And he was one of the few people, that essentially knew everything there was to know about the rockets and how to launch them. The thing I always got a kick out of Jouchoux is that he always used to grumble that he had to get down to White Sands at least once every month, because that was the only place he could get a decent flat top haircut. He couldn't get a good military cut in Boulder.
Right. Rick is here. Rick spent a lot of time with Fred.
Director of LASP for a while as well.
Well, there were, in essence, if you would, 3 directors
What?
at different
Was the interim
times.
director.
There was, yeah.
So there were like 3 directors. There was Rentz, who was the science director, Will Schussen, who was sort of the technical director, and Frank Weiss, who was the financial guy. And so they were sort of a triumvirate, a troika in management. And then, of course, when Barth came in, he took all those positions, essentially. You know, one of my stories about Charles Barth was that we were hiring someone to do orbit analysis on SME. John Calley, who I'd worked with Pioneer Venus, he was out at Ames. I coerced him to come out and work with us. So John came out, and he and I sat down with Barth for an interview. And one of the first things John said was, you know, I don't really get a good understanding of what the LASP organizational structure is. And without missing a beat, Barth picked up the phone list from the desk and handed it to him, which had his name on top as director and everybody else listed alphabetically. That was essentially the true Charles Barth vision of LASP in the early days.
I'd like to go back to your question about Fred, because I think one of the stories he delighted in telling was the time he went to Mexico to give a seminar about the rocket research that we were doing. And he had this nice little rocket model, and it had, you know, the little instrument that came out of the nose cone, and it was a great little model. And it was just big enough that when he went to pack up to come back home, he put his alarm clock in it. And he got to the border, and this model was ticking. And he had one heck of a time getting that alarm clock out of that model to show them that it was okay. But love to tell that story.
Other questions?
I'll comment on Fred. And Rick probably and some of you could probably back it up, but I heard, I guess after he passed away, there was something written about his life and what he did at LASP. And they were so busy at LASP or UAL at the time. He was a graduate student, and they were so busy, he decided not to finish graduate school and just become the director. So he went from grad student without getting a degree and became a director.
Yeah, so the story Fred told me was that he was a grad student, and when Stacy Knighty Jackson left to start Ball Brothers, he came into work one day, and their offices were empty. And it was just Ransom and a few other engineers.
So he assigned himself? He assigned himself to be?
Well, Rents needed help, and so I think he just started helping out, and then it just kind of turned out that he became the operations leader. Okay. So stopped going to school and became the operations leader.
Jim?
Yeah, so I've got a question. I was hoping Larry would be here too, but that's okay because Ian's here. So we talked a little bit, you guys talked a little bit about visualization, and one of the things I remember about Charles Barth is, you know, to the last days that I saw Charles, he was excited about, he would walk down the hall with something and say, look at this. But you guys were involved in visualization pre-computers. And so, this goes to Dave Stern also. And so IDL came along. I remember, and Fred Wilsusen and Bill McClintock and Bob Steele were kind of all involved in this. I remember when IDL came along and the realization of the value of IDL as a tool. There was on the planetary rocket with Bill doing some control systems design. We realized, well, since then, Grant Lab's overtaken you guys, but that's a different story. But we realized the value of this tool and used it just tremendously. But so Ian, do you have a moment in time where you did something using IDL during a mission, post-mission, where you said, wow, look what I can do. Look how I can now see what this, what was your epiphany?
Well, it was spread over about a decade because when I got here, people talked about delivering decks and tolerance cards to the window. In Pittsburgh, at the post doc, I had to walk a quarter mile to another building to do that. So
And people have said the first thing that arrived at last was the wine, and then there were HP calculators and PDP-8s and PDP-11s and VAXs. And so it was a progression. And I always thought that the two tremendous concepts that Barth had when he came here from JPL, he had gotten tired of the JPL system, but that's a whole other story. But he brought with him the ideas that students were very bright and unprejudiced, and they could do things that high-priced engineers could do if they got into a committee and worked on it. Students could do it just off the top of their heads. And so all the students who've been here at LASP, for decades now, are here because of that vision that he had, that not only were students smart, but of course they were cheap, and that also helped. And the other idea was the value of the miniaturized computers, the one that you could sit with eventually on your desk and do whatever it is you wanted. And Dave came from the University Computing Center to work as a Fortran programmer for me. And the way I tell it is that after 6 months, he found something more interesting, and the rest is history. And so all of the students that came in the late 60s and early 70s and worked on the miniature computers and their languages, that was every time something new came along, it was, wow, look what we can do with this. And it just came in one after the other.
I have some very fond memories of sitting with Barth at those display terminals in the analysis room, and a lot of times he'd be typing in things, but then he'd have me come over and say, well, what have we need something to the least squares fit of this to that, or something like that. And then I'd come back a couple days later, and then he would be there, and he just loved typing on those computers.
He was very innovative.
What he was doing was figuring out what he needed.
Right.
And he'd tell you what he needed, and you would give it to him. Yeah. And the whole interactive language is built up that way. They were driven by what that particular scientist in particular wanted, but also others contributed. And the ideas were implemented and executed by all you guys.
It was really fun working with him and all.
So Jim, I'll give you a couple of examples of what you were talking about that actually involved Ian, and they were both on Pioneer Venus. So we had a student who worked closely with me on Pioneer Venus, Larry Gates, and Larry one day was sitting down doing some analysis on some of the data that we had, and I think we had an HP display that had like 16 gray, or in this case green levels that you could look at. So we were looking at some data on there, and the data were taken on the night side of Venus, so we didn't expect to see anything. And all of a sudden there's this big bright blotch. And so Larry points it out to me and says, well, what's that all about? And I said, it's clearly a mistake. So we sat down and did some more manipulating, and couldn't get rid of the mistake. It kept popping out there. So finally we took it to Ian and sort of sheepishly said, well, what is this for real? And Ian said, you bet, that's for real. It's night air glow on Venus. So, I mean, just essentially, I don't know, maybe we would have discovered that with sort of the standard old methods of doing things, but being able to get in there and manipulate data and make mistakes, that sometimes pays off big time. Another one that I remember with Pioneer Venus is that, correct me if I'm wrong, Ian, but I think it was Barth who had met, maybe on an airplane, this guy who worked for a geosciences exploration company here in Boulder called InfoMap, and it turned out they had a fancy plotter that could plot out color images, which today of course would be nothing. You could do that on your iPad, but back then was very unique. So we took some of the early UV data, cloud images of Pioneer Venus, and one night after dinner we convened over there, Ian and I and Barth, and my wife was actually with me as well, and we handed them a tape, and they ran off the image on their plotter, which is on the issue of the Science magazine that was the first results of Pioneer Venus.
Well, I think another thing that Charlie Barth, he liked visualization. And he had a smart student by the name of Ken Mancock who was doing all kinds of little good electronic things, like the Go things that you put on your helmet now. So he was doing some of those. But he was also very good at programming. And he knew how to make Google display things. And so he was showing Barth one day about how he could look at his Barth house on Google. And it just clicked on me. He said, well, why, Chris and I were just reviving the Mariner 9 data. He said, well, Barth says, well, why don't we put the Mariner 9 data on Google? And so Ken went off and he did his magic, and pretty soon we had Mariner data on Google Mars. And it was just a real hit. He was just very good at visualizing what people needed to see to understand the data, how to do that.
One thing about Charles Barth always drove me crazy, and that was, I consider myself a techie and an early adopter, so I always had the first of anything, with maybe one exception, and that is that Barth always seemed to have the whatever it was, he always had it, several weeks or several months before I got it.
Any other questions? We'd like to thank all of you for all you've done for LASP, for coming to this event, for preparing for it. Phil, thank you very much for the plaque. You're welcome. And hopefully you can stay and mingle a little bit. There's still, looks like we haven't had enough students walking by to take all the cookies. So there's still cookies left out there and coffee. If you want to talk some more to the panel, I'm sure they'd be happy to do that. So thank you very much.